Hi, and welcome to Module 8, the last module of Lecture 11. Now, in the previous modules in this lecture, we discussed first abstract topics of linear algebra and vector spaces and linear independence and so on. Then we moved on later to solving systems of simultaneous equations, some more concrete applications. In this last module, we're going to put those together and see how these techniques apply to everyday practice in statistics and game theory. Now, in the book, we spent more time looking at stats and less time in game theory in this chapter. To give you some variety, we'll do the reverse here in this module. Okay, so let's start with stats, though. Recall that we first introduced a linear model like this, and then showed how we could optimize the squared error, epsilon squared, to minimize that error in order to find the optimum value of beta. Then in the last lecture, and that was back in the lecture on optimization. Now, in the last lecture we just finished, the previous lecture, we then looked at the analog example to that, where y is a vector consisting of the data points on the dependent variable. X is a matrix corresponding to the data on the independent variable, with each column being its own, being all the data points for each of a series of independent variables. Beta being the coefficient vector, and epsilon again being the error vector. And we said that you could find the optimal beta as x transpose x inverse x transpose y. Now, this thing, we went through and we calculated it. We put some made up data in there for x's and y's, and we showed how you can actually calculate in practice. Now, in practice for real, you usually use a computer for that, but it's useful to be able to understand how it comes about. And also in some classes, you will actually go through and calculate that by hand, and it's good practice to do that anyway. Okay, so that's what we did before. What new can we get out of what we did this time? Well, consider x. X is your data matrix, right? It has all the data on all your independent variables. But what if it's not the right shape? What do we mean by that? Well, what if, first of all, there are too few rows compared to the number of columns? We know in that case there'd be too few rows to actually solve for the number of columns, right? Viewing this as a set of equations. And we're not going to be able to actually compute coefficients for all the independent variables. We just have simply too few data points. So this is the sort of origin of the common solve. You have to have at least as many data points as you have variables, independent variables, or you're not going to get anywhere. Now, that's really not much of an issue usually. You usually have many, many more data points than variables, so that's not really an issue. But be aware that where that's the origin of this comes from. Second is, what if the column rank, so the number of linearly independent columns, is less than the number of columns you have? Well, in that case, what you have is multiclinearity. You can make using a combination of some number of columns, you can get the last column, or any column really, and at least one of the columns is a combination of the other columns, in which case you actually have fewer data points than you think you do. You have fewer variables, rather. You have fewer independent variables than you think you do. You have to go back to the drawing board because there's a big problem in your data set. You think you have more variables than you do, and what that leads to is an inability to actually estimate beta properly, and you can't identify it, and you need to go back to the drawing board because when you have multiclinearity, you're going to have misestimation of your beta and have issues with identifying correctly. Anyway, so that's that. That's for stats. In the book, we actually go through and talk about proving that OS is blue. Using these kind of things. Don't worry too much about that. I should say, not to worry too much about that. We're not going to do that here in the course itself, in the module itself, because we did it in the book already. But if you want to read it, and I advise you to do that, don't worry about that. Go back and take a look at the book and get that example. But that's it for this one. For a little longer one about game theory, now usually you have two or more players in a game. Let's consider a game in which two players are roughly cooperative, but one might get more or less of a benefit for cooperation than another one. So let's say you have two individuals, say, interest groups who want to get some person elected. And let's say they expect to get some benefit out of their contributions to this person, equal to their actual contribution to that person, right? So let's say if you contribute X dollars or time or whatever, you expect to get x back again, and if you're the second person, you expect to get y back again. So this is the utility for player 1, and this is utility for player 2. Now, what if you get some cooperative benefit? What if the other person contributes, you get an extra benefit for that fact? Let's say person 1 has another term like this. That means the more player 2 contributes, y, the more benefit player 1 gets from contributing itself. Because the bigger y is, the more x increases one's utility. Same thing for player 2, but let's say player 2 has some difference in cooperativeness, some different benefit, beta. And beta can be less than 1 or greater than 1. If beta is less than 1, player 2 gets less benefit for cooperation with player 1. And if beta is greater than 1, player 2 gets more cooperation more benefit for cooperation than player 1 does. And let's say they all have some cost to contributing, otherwise they just contribute forever. So let's say they both get a quadratic minus here representing increasing costs of actually contributing. We can now ask how much in equilibrium should each contribute to this campaign. Well, the first step we learned in calculus. Now, if you haven't had calculus yet, because you skipped past that part, don't worry. This example will wait for you. You can just believe me when I finish doing it. If you have had it, this is good practice. So first, you're going to maximize player 1's utility. That's going to be 1 plus y minus 2x. And that's going to equal to 0. And player 2's utility, going to maximize as well. It's going to be, with respect to y this time, it's going to be 1 plus beta x minus 2y. So pretty symmetric. So this is as far as we could go if we couldn't actually solve simultaneous systems of simultaneous equations. Right? We could maximize each individual's utility, but not figure out what the joint equilibrium is. Well, now we can do this though. Now again, I said earlier on in this lecture that I like substitution better. I'm going to do it here. It seems easier. Let's use the first equation, and rather than solve for the equilibrium x, let's actually solve for an easier one, which is y. So here y is going to have to equal 2x minus 1. Now I can plug y in using substitution to this one, and we get 1 plus beta x minus 2 times 2x minus 1. I should say these are stars in this case, but it doesn't actually matter. So we get that. Now we can add it all up, and we get, and this equals 0. We get that 1 plus beta minus 4x plus 2 equals 0, or x equals 3 over 4 minus beta. And there is x. Sorry, x star. Okay. So the equilibrium value of x, player 1 should contribute exactly that amount. Before I interpret that, let's do y first. To get y, we can plug back into here, back substitution, and we find that y equals 6 over 4 minus beta minus 1. You can make minus 1 into 4 beta over 4 beta. We'll minus that. And that implies y star is going to equal 2 plus beta over 4 minus beta. There you go. We use the methods of solving systems of simultaneous equations to figure out the equilibrium actions of both player 1 and player 2, given they're simultaneously maximizing their individual utilities, which happen to depend on the other person's actions, on each other's actions. Now, what does this mean? Well, you can actually see what's happening pretty easily. Beta here, if beta is 1, then x equals 1 and y equals 1. They both contribute 1. They both get identical benefit for cooperation, and therefore they both contribute the same amount in equilibrium. Not surprising because they have the same utility functions, basically. What if beta is less than 1? Well, let's say in the extreme case, beta is a half. Sorry, beta is 0. So person 2 does not care at all about cooperation, gets no value of it. Well, person 1 contributes 3/4. You plug there, so 3/4, and person 2 contributes 1/2. So person 2 gets no benefit from cooperation, contributes only what that person would contribute independent of this term, which is a half, that's the maximum in that case, and end up contributing less. Person 1 who does care about cooperation contributes more than the half that it would contribute, that he or she would contribute on his or her own, and contributes 3/4, taking advantage of this gains to cooperation. What if beta is the opposite, 2? Well, in that case, player 2 contributes 4/2, which is actually 2. And player 1 contributes 3/2, which is 3/2. So now they both contribute more than they would individually, and even more than they would have. And player 1, even more than player 1 would have given player 2's actions, and now player 2 contributes more. So again, in other words, player 2 contributes a lot more now because player 2 is really benefiting from player 1's contribution as well. But player 2 also contributes more because now player 1 now contributes more because player 2 has more incentive to contribute, which increases the marginal gains for player 1's contributions. So they both have cooperatively higher marginal gains for cooperation, and they both contribute more. Higher marginal gains for contributions. So they now both contribute more and get higher contribution from each person, but player 2 contributes more than player 1 in this case. So this is sort of the standard kind of argument you can make in game theory. This actually gives you a little preview of what we're going to be talking about when we do comparative statics in the very last lecture in this course, the last part of the class, where we look at how changing parameters can change equilibrium values and so on. But there you go. There's an example of solving simultaneous equations in game theory. This comes up all the time in game theory. And obviously using data matrices comes up all the time in stats as well. So you'll see these kind of things a lot. So linear algebra is a very common, very useful tool in all sorts of aspects that you see every day. And that finishes this lecture. In the next lecture, what we're going to do is cover a couple of topics that are a little less common, a little less frequently used in everyday sort of use in social sciences, but do relate to topics that are increasingly seen in political science and all social sciences, particularly political science and we kind of social to a degree. And they are eigenvalues and eigenvectors, which would turn up in things like time series and network analysis, and Markov chains, which turn up in Markov chain Monte Carlo simulations and also in Markov perfect equilibrium and Markovian processes that are seen in boundedly rational games and boundedly rational models and so on. So all those more advanced topics occur in the next lecture. If you feel comfortable now and you want to move on from here, you can safely move on. The next lecture stuff is more advanced and is not the kind of stuff that you typically are expected to know before going on into a bunch of your class, in a bunch of early classes, but will be seen in later classes. So if you want to get a head start on it, go right ahead right now. Otherwise, that lecture will be waiting for you when you get to it. Thank you very much.